Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. So, picture this. It's 1783, and there's this English clergyman named John Michell sitting in his study, probably by candlelight, thinking about stars. Not unusual for a reverend in those days. Many clergy were also natural philosophers, what we'd call scientists today. But Michell was thinking about something that would absolutely blow your mind. He was imagining stars so massive, so incredibly dense, that even light itself, travelling at 186,000 miles per second, couldn't escape their gravitational pull. Think about that for a second. Light, the fastest thing in the universe, trapped like a fly in cosmic amber. Michell called them dark stars, and honestly, the name gives me chills every time. Now, here's what's wild about this moment in history. Michell was working with Newton's physics, classical mechanics, stuff that wouldn't fully make sense of what he was describing for another 130 years. He was basically using 18th century math to accidentally predict one of the most extreme objects in the universe. It's like trying to describe a smartphone using only knowledge from the horse and buggy era. But here's the crazy part. Nobody really paid attention to his letter. It got filed away, forgotten, gathering dust while the world moved on. Michell died, never knowing he'd glimpsed something that would haunt physics for centuries. Fast forward to 1915. The world is tearing itself apart in the trenches of World War I, and there's this German physicist named Karl Schwarzschild. Picture him, brilliant mathematician, serving on the Russian front, calculating by lamplight in muddy dugouts while artillery shells explode overhead. Most people in his situation would be focused on survival. Schwarzschild, he's solving Einstein's brand new field equations. Einstein had just published his theory of general relativity, and it was revolutionary stuff. Space and time weren't separate things anymore. They were woven together into this fabric called space-time, and massive objects could bend and warp it. Imagine stretching a rubber sheet and dropping a bowling ball in the middle. The sheet curves around the ball, and if you roll marbles nearby, they'll spiral toward it. That's basically how gravity works, according to Einstein. So, Schwarzschild takes these equations and asks a simple question. What happens around a perfectly spherical, non-rotating massive object? Sounds straightforward, right? Well, when he worked through the math, he found something that shouldn't exist. The equations predicted a point where space and time simply ended. Not gradually, not with some cosmic fanfare, but just stopped. A boundary where the normal rules of physics broke down completely. Inside this boundary, escape was impossible. Outside, you might have a chance. The boundary itself? Schwarzschild calculated its exact size based on the object's mass. For something with the mass of our Sun, this boundary would have a radius of about 2 miles. Picture the entire mass of our Sun, 991 billion tons, compressed into a sphere smaller than Manhattan. The gravitational field at that boundary would be so intense that space-time itself would curve back on itself. Here's what gets me about this story. Schwarzschild solved these equations while literally dodging bullets. He mailed his solution to Einstein in December 1915, and then, tragically, died of an autoimmune disease contracted on the front lines just a few months later. He never lived to see how his solution would revolutionize our understanding of the universe. Einstein read Schwarzschild's work and was genuinely disturbed by it. The great physicist, the man who'd revealed that space and time were flexible, refused to believe his own equations. He spent years trying to prove that these Schwarzschild singularities couldn't exist in nature. Einstein thought they were mathematical curiosities, weird artifacts of the equations that wouldn't show up in the real world. And you know what? I get it. The implications were terrifying. Schwarzschild's solution suggested there could be regions of space where matter became infinitely dense, where the curvature of space-time became infinite, where time itself would stop for outside observers. It was like finding a mathematical description of cosmic insanity. But the universe, as we've learned over and over again, doesn't care what makes us comfortable. For decades, physicists treated these objects as theoretical monsters, mathematical dragons that might exist on paper, but surely not in reality. They had names for them: gravitationally completely collapsed objects, frozen stars, space-time singularities. The term black hole wouldn't be coined until 1967 by physicist John Wheeler, and even then it was almost used as a joke. Here's where the story gets really fascinating. While physicists were debating whether these things could exist, astronomers were starting to find them. In the 1930s, a brilliant young Indian physicist named Subrahmanyan Chandrasekhar was traveling by ship to Cambridge University. He was just 19 years old, but during that long sea voyage, he worked out the mathematics of what happens when massive stars die. His calculations showed that stars above a certain mass, complex, about 1 and 4 times the mass of our Sun, couldn't just fade away quietly. They would collapse catastrophically, potentially forming exactly the kind of object Schwarzschild had described. When Chandrasekhar presented his findings to the scientific community, he was publicly humiliated by Sir Arthur Eddington, one of the most respected astronomers of the time. Eddington declared the idea stellar buffoonery and suggested there must be some natural law that prevented such absurd objects from forming. Imagine being 19 years old, having worked out one of the most important discoveries in astrophysics, and being told by the scientific establishment that you're basically talking nonsense. Chandrasekhar was so discouraged that he almost abandoned astrophysics entirely. But here's the beautiful thing about science. The universe gets to vote. And the universe was about to reveal that Chandrasekhar was absolutely right. Throughout the 1940s and 50s, astronomers kept finding strange things. Radio telescopes were picking up incredibly powerful signals from distant points in space. X-ray detectors were recording violent energy emissions that seemed to come from nowhere. And telescopes were spotting massive stars that appeared to be dancing with invisible partners. The puzzle pieces were scattered across decades of observations, waiting for someone to put them together. What astronomers were seeing were the calling cards of black holes, not the objects themselves, which by definition emit no light, but the spectacular chaos that surrounds them as they feed. You see, when matter falls toward a black hole, it doesn't just quietly disappear. It forms what's called an accretion disk, a swirling maelstrom of gas and debris that gets heated to millions of degrees as it spirals inward. This superheated material screams across the electromagnetic spectrum, producing X-rays, radio waves, and light shows that can outshine entire galaxies. By the early 1970s, the evidence was becoming overwhelming. Astronomers had found multiple candidates, massive, dark objects, whose gravity was affecting nearby stars in ways that could only be explained if they were incredibly dense. The most famous was Cygnus Zone, an X-ray source where a blue supergiant star was clearly orbiting something invisible that weighed about 20 times more than our Sun. Stephen Hawking was so confident that Cygnus Zone was not a black hole that he made a famous bet with fellow physicist Kip Thorne. If it turned out to be a black hole, Hawking would buy Thorne a subscription to Penthouse magazine. If it wasn't, Thorne would buy Hawking a subscription to Private Eye. In 1990, as the evidence became undeniable, Hawking conceded the bet. But here's what really gets me excited about this story. We're not just talking about finding weird objects in space. Black holes represent something profound about the nature of reality itself. They're places where space and time behave in ways that challenge our most basic intuitions about how the universe works. Near a black hole, time literally runs slower. If you could hover just outside the event horizon and watch the rest of the universe, you'd see everything happening in fast forward. Centuries would pass like minutes. Galaxies would evolve before your eyes. Meanwhile, to observers far away, you'd appear to slow down and freeze, your image getting redder and dimmer but never quite disappearing. Inside the event horizon, TU9, that boundary Schwarzschild calculated, D9, space itself falls faster than light. It's like being caught in a cosmic waterfall where the water is space-time itself, and no matter how fast you swim upstream, you're still going over the falls. And at the center, a singularity, a point where our understanding of physics completely breaks down. All the mass that formed the black hole gets compressed to infinite density. The curvature of space-time becomes infinite. Our equations start spitting out infinities, which is basically math's way of saying, I give up. Now, you might be thinking, okay, this is all fascinating in a terrifying way, but why should I care? These are exotic objects in distant space, right? They don't affect my daily life. Well, here's the twist that'll blow your mind, and we'll explore this much more as our journey continues. Black holes might be the reason you exist at all. Every atom in your body except hydrogen was forged in the nuclear furnace of a star. But those stars only existed because supermassive black holes at the centers of galaxies shaped how matter could clump together in the early universe. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, it all exists because black holes helped sculpt the cosmic conditions that made star formation possible. These aren't just cosmic monsters lurking in the darkness. They're architects of the universe, gardeners of galaxies, and possibly the key to understanding the deepest mysteries of existence. From John Michel's dark stars to Schwarzschild's impossible equations to today's direct observations, we've been slowly piecing together one of the most remarkable stories in science. We've learned that the universe is far stranger and more wonderful than our ancestors could have imagined, but our journey is just beginning. Next time, we're going to dive into one of the greatest detective stories in astronomy, the how do you find something that by definition cannot be seen? How do you track down invisible dragons hiding in the cosmic dark? The hunt for black holes required detective work spanning decades, brilliant insights from 19-year-old physicists, and eventually, technology that could capture the uncapturable, the first photograph of a black hole's shadow. It's a story of human ingenuity, cosmic patience, and the moment when we finally proved that the universe's most impossible objects are not only real, but everywhere. So stick around. Trust me, you're not going to believe what we found lurking out there in the dark. So how exactly do you hunt for something that's completely invisible? I mean, think about it. Black holes got their name because they're literally black. They don't emit light, they don't reflect light, they swallow light whole. It's like trying to find a hole in the night sky by staring really, really hard at the darkness. But here's where human ingenuity gets absolutely brilliant. Sometimes the best way to find something invisible is to look for what it does to everything around it. And black holes? Well, they're not exactly subtle about their presence. Picture this. It's 1964, and NASA launches a rocket carrying a bunch of Geiger counters. Not looking for black holes, nobody was even sure they existed yet, but just scanning the sky for X-rays. Back then, X-ray astronomy was brand new. We'd barely started looking at the universe through anything other than visible light. The rocket finds something incredible, violent, screaming X-rays coming from a point in the constellation Cygnus. They name it Cygnus Zone, and it's pumping out more X-ray energy than anything they'd ever seen. But here's the weird part. When they point optical telescopes at the same spot, they see a perfectly normal blue star. Now, normal stars don't just randomly blast X-rays into space. I mean, our sun produces some X-rays, but nothing like this. Cygnus Zone was producing X-rays at levels that were just insane. Something was seriously wrong with this picture. Enter the cosmic detectives. Astronomers started watching this blue star more carefully, and they noticed something fascinating. It was wobbling, not randomly, but in a perfect, predictable pattern, like it was dancing with an invisible partner. You know how when you're spinning around with someone, you both lean back and circle around a point between you? That's exactly what this star was doing. Every 5.5 days, it would complete one orbit around, and nothing. At least, nothing they could see. But here's where the math gets really exciting. By watching how the star moved, astronomers could calculate the mass of its invisible companion. And when they did the calculations, holy cow! The invisible object weighed about 20 times more than our Sun. 20 solar masses, completely dark, in a space smaller than a large city. What else could it be? Still, the scientific community was cautious. Maybe it was some kind of weird neutron star. Maybe their calculations were wrong. Maybe there was some exotic type of matter they hadn't discovered yet. The evidence was compelling, but not quite smoking gun material. Then, in the 1970s, things got really interesting. Astronomers realized that the X-rays weren't coming from the black hole itself. They were coming from the spectacular light show happening right next to it. Picture this cosmic scene. You've got this massive blue star, and it's so close to the black hole that the black hole's gravity is literally stealing material from it. Gas streams off the star in long, graceful ribbons, spiraling down toward the black hole like water going down a cosmic drain. But here's the incredible part. As this material falls inward, it speeds up a lot. We're talking about gas moving at significant fractions of the speed of light, all crammed together in this swirling disk around the black hole. The friction between all these particles racing around at insane speeds heats everything up to millions of degrees. At those temperatures, matter doesn't just glow, it screams. It produces X-rays so intense they can be detected from thousands of light-years away. The black hole itself might be invisible, but its dinner plate is one of the brightest things in the universe. Now, you might be wondering about that 19-year-old I mentioned earlier, Subrahmanyan Chandrasekhar. His story is one of those beautiful examples of how science works, even when it doesn't seem like it's working at all. Remember, when Chandrasekhar presented his calculations about massive star collapse in the 1930s, he was essentially laughed out of the room by Arthur Eddington, one of the most respected physicists of the time. Eddington was so influential that his dismissal basically killed any serious discussion of black holes for decades. But Chandrasekhar didn't give up on science, he just moved on to other problems. He made groundbreaking contributions to stellar structure, atmospheric physics, even mathematical physics. He kept doing brilliant work, while the universe slowly proved him right. In 1983, 50 years after his original paper, Chandrasekhar finally won the Nobel Prize in Physics. The citation specifically mentioned his work on the evolution and collapse of stars. Sweet vindication, right? But here's what I love about Chandrasekhar's response. He was gracious. No, I told you so. No bitterness about the decades of dismissal. Just quiet satisfaction that the truth had finally caught up. But let's get back to our cosmic detective story, because by the 1980s, astronomers weren't just finding one or two black hole candidates. They were finding them everywhere. The technology kept getting better. Space telescopes could detect X-rays without having to peer through Earth's atmosphere. Computer processing power meant they could analyze the complex orbital mechanics of binary star systems, and the patterns kept repeating. Massive, invisible objects with telltale accretion disks screaming in X-rays. Then came one of the most ambitious observational projects in astronomy history. In the 1990s, a team led by Andrea Ghez at UCLA and Reinhard Genzel in Germany started something that sounded absolutely crazy. They were going to watch individual stars orbit the center of our own galaxy. Now, the center of the Milky Way is about 26,000 light-years away, hidden behind clouds of dust and gas. It's like trying to watch ants crawl around on the sidewalk from the top of Mount Everest at night in a fog. The technical challenges were insane, but Gez and her team had a secret weapon: adaptive optics. Basically, they figured out how to use computers to constantly adjust their RUVA telescope mirrors hundreds of times per second, compensating for the blurring effects of Earth's atmosphere. Suddenly, they could see individual stars in the galactic center with incredible clarity. What they found was absolutely mind-blowing. There were stars racing around the galactic center at speeds that should be impossible. We're talking about 5,000 miles per second, fast enough to cross the entire United States in about a minute. Some of these stars had orbits so extreme that they'd swing from distances farther than Pluto all the way down to just a few times the distance from Earth to the Sun. For 25 years, Gez and her team tracked these stars. They watched them complete entire orbits around. Nothing. Well, nothing visible. But the math was inescapable. There had to be something at the center of our galaxy, weighing 4 million times more than our Sun, compressed into a region smaller than our solar system. 4 million solar masses, in a space the size of our solar system. What else could it be but a supermassive black hole? In 2020, Andrea Ghez won the Nobel Prize in Physics for this work. She became only the 4th woman ever to win the Physics Nobel, and the first to win it for astronomical observations. But more importantly, her work proved beyond any doubt that supermassive black holes are real, and there's one sitting right at the heart of our own galaxy. But wait, there's more. Because in 2019, we achieved something that should have been impossible. We took a photograph of a black hole. I know what you're thinking. How do you photograph something that doesn't emit light? Well, you don't photograph the black hole itself, you photograph its shadow. The Event Horizon Telescope is one of the most ambitious scientific projects ever attempted. It's not actually a single telescope. It's a network of radio telescopes scattered across the entire planet, from Hawaii to Antarctica to Spain. When they all observe the same target simultaneously, computer processing can combine their signals to create a virtual telescope the size of Earth. Think about that for a second. A telescope the size of our entire planet. The resolution is so incredible that if you put this telescope in New York, it could read a newspaper in Los Angeles. And they pointed this impossible instrument at Galaxy M, 87.55 million light-years away. What they captured was one of the most important images in the history of science, a perfect ring of fire surrounding absolute darkness. The glowing accretion disk of superheated matter spiraling around a black hole, 6.5 billion times more massive than our Sun, with the black hole's shadow clearly visible in the center. The image matches Einstein's predictions from over a century ago with frightening accuracy. The ring is almost perfectly circular, glowing brightest on one side where the matter is racing toward us at nearly the speed of light. And in the center, pure black. The point of no return made visible. But here's what really gets me excited about these discoveries. They're not just confirming what we theorized. They're revealing that black holes are everywhere, and they come in sizes we never expected. We found stellar mass black holes, remnants of massive stars, weighing anywhere from a few times to 100 times our Sun's mass. We found supermassive black holes at the centers of galaxies weighing millions or billions of solar masses. But we've also found intermediate mass black holes weighing thousands of solar masses that theoretically shouldn't exist. And then there are the primordial black holes, possibly formed in the first fraction of a second after the Big Bang, before the first stars ever existed. Some could be smaller than atoms but weigh as much as mountains. Others could be wandering through space right now, invisible and undetected. Even stranger, we've discovered that black holes sing. The supermassive black hole at the center of the Perseus galaxy cluster produces sound waves, actual acoustic vibrations traveling through the hot gas around it. The note? B flat, 57 octaves below middle C. It's been playing this note for over 2 billion years, making it the deepest bass note in the universe. But perhaps the most mind-blowing discovery is just how important black holes are to the universe itself. Remember, we started this journey thinking of them as cosmic monsters, devourers of light and matter, but it turns out they're also cosmic architects. Every large galaxy has a supermassive black hole at its center, and the mass of that black hole is directly related to the mass of the galaxy's central bulge of stars. It's like the black hole and the galaxy grew up together, each one influencing the other's development. When black holes feed, they don't just quietly consume matter. They launch jets of material at 99%, the speed of light, shooting streams of particles and energy thousands of light years into space. These jets carry magnetic fields, heavy elements, and energy that help shape how galaxies form and evolve. In a very real sense, the black hole at the center of our galaxy helped determine where and how stars could form, including the star we call the Sun. Without supermassive black holes sculpting the large-scale structure of the universe, the delicate dance of galaxy formation might never have produced the stable, long-lived stellar neighborhoods where planets like Earth could exist. So, from invisible dragons lurking in the cosmic dark, we've discovered that black holes are actually cosmic gardeners, cultivating the conditions for complexity, chemistry, and ultimately, life itself. But our journey into the darkness is just beginning, because next, we're going to take the ultimate trip. We're going to fall into a black hole ourselves and experience what it's like to cross the point of no return. Fair warning, it's going to be the most beautiful and terrifying ride in the universe. Get ready to discover what happens during your final hour as a human being. All right, let's take a trip together. But fair warning, this is going to be the most intense journey you'll ever experience, and there's no coming back from where we're going. You're approaching a stellar mass black hole, maybe 10 times the mass of our Sun. You're still far away, about the distance from Earth to the Moon, and honestly, it's beautiful. Not terrifying yet, just magnificent. The first thing you notice isn't the black hole itself, because of course you can't see it. What you see is the accretion disk, that swirling maelstrom of superheated matter spiraling inward. It's like a cosmic hurricane made of fire, glowing white-hot in the center where material is moving at a significant fraction of light speed, cooling to brilliant blues and purples at the edges. But here's where things start getting weird. The entire universe around you is beginning to change. Light from behind you is getting stretched and red-shifted, while light from ahead is getting compressed and blue-shifted. The result is that the universe starts rearranging itself into a rainbow-colored disk above and around you. This is gravitational lensing in action. The black hole's immense gravity is bending space itself, and light follows those curves. You're seeing parts of the universe that should be behind the black hole, appearing as distorted images around its edges. It's like looking into a cosmic funhouse mirror, except the distortions reveal actual distant galaxies and stars. But let's talk about what you're feeling right now, because the physics is about to get very personal. At this distance, about 240,000 miles from the black hole, you're starting to notice something subtle. Your feet feel just a tiny bit heavier than your head. It's barely perceptible, like the difference between standing on Earth and standing on a slightly more massive planet. This is the beginning of tidal forces, and they're going to become very, very important in the next hour of your life. See, gravity isn't actually a force pulling you toward the black hole. It's the curvature of space-time itself. And just like a curved slide at a playground, the steeper the curve, the faster you accelerate down it. The problem is, Your feet are slightly closer to the black hole than your head, so they're experiencing slightly stronger gravity. Right now, it's no big deal, but as you fall closer, that tiny difference is going to grow exponentially. Let me put this in perspective for you. At the distance of our moon from Earth, the tidal force between your head and feet would create a difference of about 1/10,000,000th of Earth's gravity. Barely measurable. But black holes are different beasts entirely. As you fall inward, picking up speed, the numbers start getting serious. At about 60,000 miles from the black hole, that gentle tug becomes noticeably uncomfortable. The difference in gravitational pull between your head and feet is now equivalent to about 10 pounds of force trying to stretch you apart. Still survivable, but definitely not pleasant. You'd feel like someone was gently but persistently trying to pull your feet away from your body. It's the cosmic equivalent of being on a medieval torture rack, except the rack is space and time itself. But here's where your journey takes a fascinating turn into the realm of time itself. You see, time isn't flowing the same way for all parts of your body anymore. Einstein's general relativity tells us that time moves slower in stronger gravitational fields. Since your feet are experiencing slightly stronger gravity than your head, time is literally moving slower for your feet than for your head. We're talking about tiny fractions of seconds over the course of your fall, but it's measurable. Your brain, trying to coordinate your body, starts experiencing something no human has ever dealt with before. Different parts of your nervous system are operating at slightly different rates. Signals from your feet take a little longer to reach your brain, not because of distance, but because time itself is running slower down there. At 30,000 miles from the black hole, things are getting genuinely uncomfortable. The tidal force is now equivalent to about 100 pounds trying to stretch you apart. You'd feel like you were hanging from your arms while someone pulled on your legs. Still within the range of human experience, but definitely painful. And the visual effects are getting more extreme. The universe above you has compressed into an increasingly bright ring, while the blackness ahead grows larger. Light from the cosmic microwave background, 1.5, the afterglow of the Big Bang itself, is getting blue-shifted into visible light. You're literally seeing the birth of the universe as a faint glow around the black hole's shadow. But let's fast forward to the really dramatic part, because at about 15,000 miles from the black hole, your body reaches what scientists poetically call the tidal radius. This is where the difference in gravitational force between your head and feet becomes genuinely dangerous to human physiology. The stretching force is now equivalent to about 1,000 pounds. Your spine is experiencing stresses far beyond what human anatomy can handle. Your blood is having trouble flowing from your feet to your head against the differential gravity. Your inner ear, trying to maintain balance in this impossible situation, is sending confused signals to your brain. This is where the famous spaghettification begins, though it starts more subtly than the dramatic name suggests. You're not instantly turned into pasta. It's more like being placed in a cosmic taffy-pulling machine that's slowly ramping up the pressure. At 7,000 miles from the black hole, the tidal force reaches about 10,000 pounds. This is beyond the breaking point for human bone and tissue. Your body begins to deform, stretching vertically while being compressed horizontally. It's a grotesque ballet of physics playing out with your anatomy. But here's something remarkable that's happening simultaneously. You're witnessing one of the most spectacular light shows in the universe. As you fall closer to the black hole, you're encountering light that fell in before you. Photons that have been orbiting the black hole in increasingly tight spirals, some for minutes, others for hours or even days. You're seeing the ghostly after-images of anything that fell in before you, frozen in time like cosmic photographs. If another person had fallen in ahead of you, you'd see multiple images of them, proximal, some recent, some from much earlier in their fall, all orbiting around the black hole at different distances. It's like watching instant replays of cosmic history, all happening simultaneously. At 3,000 miles from the black hole, your situation becomes truly desperate. The tidal forces are now equivalent to about 100,000 pounds trying to tear you apart. No human body could survive this, but let's imagine you somehow could, because the physics gets even more incredible. Your body is now noticeably elongated, stretched into a form that would be unrecognizable to anyone who knew you. But your consciousness, assuming it could somehow persist, would be experiencing something absolutely unprecedented in human history. You're falling at a significant fraction of the speed of light now. The Doppler effects are becoming extreme. Light from the universe behind you is redshifted so far that it's disappearing into the infrared and radio spectrum. Light from ahead is blue shifted so intensely that ordinary starlight is becoming gamma radiation. You're essentially being bathed in a bath of high-energy photons created by the black hole's effect on the cosmic microwave background. If you could somehow survive the tidal forces, the radiation would probably kill you anyway, but the visual experience would be beyond words. The entire electromagnetic history of the universe is being compressed into a brilliant ring above you. You're seeing light that left distant galaxies billions of years ago, all arriving at your location simultaneously, boosted to incredible energies by your fall into the black hole. At 1,000 miles from the black hole, the tidal forces reach about 1,000,000 pounds. Your body, if it still existed as a coherent structure, would be stretched into something resembling a long, thin noodle. The technical term is spaghettification, and while it sounds almost comical, the reality is both beautiful and terrifying. You've become a stream of matter following the curvature of space-time down toward the singularity. Your atoms are still there, still held together by electromagnetic forces, but arranged in a completely different configuration than anything that has ever been called human. And yet, the journey isn't over. You're approaching the event horizon, of that boundary we've talked about, the point of no return. But here's the really wild thing. From your perspective, crossing the event horizon isn't dramatic at all. There's no wall, no barrier, no sudden change. You pass through this cosmic boundary as smoothly as walking through an open doorway. You might not even notice the moment it happens, except for one thing. Every direction now points the same way, inward. Behind you, the entire history of the universe is compressed into an increasingly bright ring of light. Ahead of you lies only darkness, not the absence of light, but a region where light itself is falling inward faster than it can escape. You've crossed the point of no return, and there's something profound about this moment. To outside observers, you appear to slow down and freeze at the event horizon, your image getting redder and dimmer until it fades away. But from your perspective, time flows normally. You've simply entered a region of space where the exit doors have been removed. The funny thing is, for a supermassive black hole, say, the one at the center of our galaxy, crossing the event horizon would be almost gentle. The tidal forces at the event horizon of Sagittarius A star, our galactic center black hole, are actually quite mild. You could cross the boundary in comfort, only to be torn apart much later as you approach the singularity. But we're dealing with a stellar mass black hole, where the event horizon is much smaller and the tidal force is much more intense. For you, the spaghettification process is nearly complete by the time you cross that invisible boundary. At 100 miles from the center, you're no longer recognizable as human in any conventional sense. You've been stretched into a stream of fundamental particles, but those particles still carry the information that was once you. Every atom that made up your body is still there, just rearranged. The visual experience, if consciousness could somehow persist through this transformation, would be indescribable. You're seeing the universe's entire electromagnetic spectrum compressed into a ring of impossible brightness above you. The energy density of light around you is approaching that of the Big Bang itself. At 10 miles from the center, even the atoms that once composed your body are being subjected to forces that dwarf anything found elsewhere in the universe. The gravitational gradient is so steep that the electromagnetic forces holding your atoms together are starting to struggle against the differential gravity between one side of an atom and the other. You're approaching the singularity now, that point where all the mass that formed the black hole is theoretically compressed to infinite density. Our equations break down here. Physics, as we understand it, simply stops. In your the moments, you're experiencing something that no theory can fully describe. Are you being added to a point of infinite density? Are you encountering some kind of quantum foam where space and time themselves become meaningless? Are you somehow passing through to another region of space-time entirely? We don't know. At the singularity, general relativity predicts infinite curvature, infinite density, infinite tidal forces. But infinities in physics usually mean we're missing something important. Quantum mechanics suggests that at the smallest scales, space and time might not be smooth and continuous, but granular, made of discrete units too small to measure. Maybe the singularity isn't a point at all, but a region where our normal concepts of space and time simply don't apply. Maybe it's a doorway to something else entirely. Or maybe it's exactly what the equations suggest, a place where the story of matter and energy comes to an end. What we do know is this: from the moment you began this journey to your final approach to the singularity, you've experienced something that represents the absolute extreme of what physics allows. You've been stretched across space-time itself, witnessed the entire electromagnetic history of the universe, and approached the very boundaries of our understanding of reality. Your atoms, the calcium in your bones, the iron in your blood, the carbon in your DNA, have taken a journey to the very edge of existence, and in some sense that's beautiful. You've become part of something larger than human experience, larger than Earth, larger than our solar system. You've joined the fundamental dance of matter and energy at the universe's most extreme frontier. But here's the thing about black holes that'll blow your mind. Crossing the event horizon is just the beginning of the weirdness. Inside the black hole, the rules of reality become even stranger than what we've just experienced. Next time, we're going to explore what lies beyond that, the point of no return, where space and time themselves behave in ways that challenge everything we think we know about the universe. We're going to discover that crossing the event horizon isn't an ending, it's an entrance to the strangest theatre in the cosmos. So here's something that's going to mess with your mind. The event horizon, this cosmic boundary that we've been talking about as the point of no return, doesn't actually exist as a physical thing. It's not a membrane, not a wall, not even a change in the fabric of space itself. It's just a line drawn by mathematics. Think about it this way. Imagine you're in a rowboat on a river and you're approaching a waterfall. There's a point upstream where, no matter how hard you row, the current will sweep you over the falls. That invisible line across the river, that's basically what an event horizon is, the point where escape velocity exceeds the speed of light. But here's the beautiful and terrifying thing. You can cross that line as gently as dipping your toe in a warm bath. Let's step back from our previous nightmare scenario with the stellar mass black hole and imagine something different. Picture yourself approaching the supermassive black hole at the center of galaxy M87, the one we actually photographed in 2019. This monster weighs 6.5 billion times more than our Sun, and its event horizon has a diameter larger than our entire solar system. At this scale, the physics becomes almost gentle. You're approaching the event horizon, and honestly, it's anticlimactic. No fireworks, no cosmic trumpets, no sudden change in the scenery. The curvature of space-time is so gradual here that you'd experience less tidal force than you feel between your head and feet while standing on Earth. You could literally cross the event horizon while reading a book, and you might not even notice the moment it happens. The only clue would be a subtle shift in how light behaves around you, and even that would be easy to miss if you weren't paying attention. But here's where things get genuinely weird. Once you cross that invisible boundary, the nature of space and time fundamentally changes. Outside the event horizon, you can point in any direction: up, down, left, right, forward, backward, and potentially head in that direction if you have enough fuel. Inside the event horizon, every direction points the same way, inward, not metaphorically, but literally. The geometry of space-time itself has been so warped that inward toward the singularity becomes as inevitable as forward through time. It's like being caught in a cosmic waterfall where the water is space itself. Outside the falls, you can swim in any direction. Once you go over the edge, there's only one way to go: down. Except in this case, down means toward the center of the black hole, and the current carrying you is the fabric of reality itself. Stephen Hawking once described it perfectly. Inside a black hole, space and time switch roles. Outside, you can move freely through space but are carried inevitably forward through time. Inside, you can move freely through time, in the sense that proper time continues to flow normally for you, but you're carried inevitably inward through space. This creates one of the most mind-bending consequences of black hole physics. Causality itself gets twisted. Normally, causes precede effects. You flip a light switch, then the light turns on. You throw a ball, then it travels through the air. But inside a black hole, the direction toward the singularity becomes time-like, meaning that moving toward the center becomes as inevitable as aging. If you somehow had magical rockets that could accelerate you at the speed of light, you still couldn't escape, because space itself is falling inward faster than light. It's like trying to swim upstream in a river where the current exceeds your maximum swimming speed. But let's talk about what you're actually seeing during this impossible journey, because the visual experience inside a black hole is unlike anything in the rest of the universe. Behind you, the entire external universe appears compressed into a brilliant ring. Every photon that was racing to catch up with you as you fell in is now arriving simultaneously, creating a blazing circle that contains all of cosmic history. You're seeing light from distant galaxies, the cosmic microwave background, maybe even light from other objects that fell into the black hole before you. But here's the really wild part. That ring is getting brighter and bluer as you fall deeper. Light that started as gentle radio waves from the cosmic microwave background is being blue-shifted into visible light, then into X-rays, then into gamma rays. You're watching the universe's baby pictures, light from just after the Big Bang, being transformed into some of the most energetic radiation possible. Ahead of you, pure black. Not the black of a dark room, but the black of a region where light cannot exist in any stable orbit. Every photon that enters this region joins you on the one-way trip to the singularity. And yet, you might not be alone in this cosmic theatre. Light that fell in before you, maybe from stars that were consumed months or years ago, is still here, falling alongside you like ghostly companions. If another explorer had preceded you into the black hole, you might see multiple images of them, recent images from just before you arrived, and older images from earlier in their fall, all frozen in the complex geometry of space-time. It's like a cosmic museum, where every moment of the black hole's feeding history is preserved in light, all falling together toward the unknowable center. Now, if this black hole is rotating, and most black holes are, things get even stranger. Rotation creates something called the ergosphere, a region outside the event horizon where space-time itself is dragged around like honey, stirred with a spoon. In the ergosphere, staying in one place relative to the distant universe becomes impossible. Space itself is spinning, and everything in it gets dragged along for the ride. It's like trying to remain motionless while standing on a cosmic merry-go-round. The very fabric of reality is in motion. Inside a rotating black hole, the singularity isn't a point, it's a ring. And here's where theoretical physics gets really exotic. That ring might be a gateway to other regions of space-time. Einstein-Rosen bridges, wormholes, passages to other universes, API, all mathematically possible inside the swirling geometry of a rotating black hole. Of course, whether you could actually survive the journey to find out is another question entirely. The tidal forces near the ring singularity would be substantial. But let's focus on something even more mind-bending: the relationship between time and space inside the black hole. From your perspective, falling toward the singularity, time flows normally. Your watch ticks at its regular pace. Your thoughts unfold at their usual speed. Your biological processes continue as if nothing unusual is happening. In your reference frame, you might spend minutes, hours, or even days falling from the event horizon to the singularity, depending on the black hole's mass. But here's the thing that'll keep you awake at night. To outside observers, you never quite reach the singularity. In fact, from their perspective, you never even finished crossing the event horizon. The last image they saw of you was frozen at the boundary, slowly fading and reddening until it became undetectable. This creates one of the deepest puzzles in physics. What really happens to information that falls into a black hole? If observers outside never see you complete your fall, does your information ever actually reach the singularity, or does it somehow remain encoded on the event horizon forever? This is the heart of the black hole information paradox, and it's been keeping physicists arguing for decades. But from your perspective, the journey continues. You're falling through a region of space where the normal rules have been suspended, where geometry becomes a kind of cosmic poetry, where the very concepts of here and there take on meanings that would have seemed impossible outside the event horizon. The mathematics describing your fall are beautiful in their complexity. The metric of space-time, the fundamental description of how distances and times are measured, becomes a symphony of differential equations that would make mathematicians weep with joy and terror. Inside a black hole, space doesn't just curve, it folds, twists, and ultimately breaks down entirely as you approach the singularity. The coordinate systems that physicists use to describe normal space-time become meaningless. Up and down, left and right, even past and future begin to lose their conventional definitions. And yet, your subjective experience remains surprisingly normal. You still feel like you, still think your thoughts, still experience the flow of time in the familiar way. The universe is revealing its most extreme behavior, and you're experiencing it from the inside like a cosmic anthropologist documenting the impossible. As you fall deeper, the external universe compressed into that brilliant ring continues its spectacular light show. You're seeing the entire electromagnetic spectrum of cosmic history, compressed and energized by your fall through curved space-time. Ancient starlight, radio waves from distant galaxies, the afterglow of the Big Bang itself, all arriving at your location with energies boosted by the black hole's immense gravitational field. It's the ultimate cosmic light show, viewable from the universe's most exclusive theater. No telescope will ever record what you're seeing. No external observer will ever witness this perspective. You're experiencing something that exists at the very boundary, between the knowable and unknowable universe. The irony is profound. Inside the most destructive objects in the universe, you might be witnessing the most beautiful phenomena that physics allows. The same extreme curvature of space-time that spells doom for any material object creates visual experiences that surpass anything else in nature. But the journey isn't over. You're still falling, and ahead lies the singularity, that point where our understanding of physics reaches its absolute limit. Whether it's truly a point of infinite density or something else entirely, it represents the place where space and time themselves might cease to have meaning. What happens when you reach that mathematical impossibility? What exists at the very heart of a black hole where our equations break down and our concepts fail? Next time, we're going to explore the theatre at the end of time itself, where physics becomes poetry and the universe reveals its deepest secrets to the only audience that can never report back. We're going to discover what lies beyond the edge of human understanding, in the place where matter and energy write their final chapter. Get ready for the most exclusive show in the cosmos. Welcome to the most exclusive theatre in the universe, where the price of admission is everything you are, and the show runs for exactly as long as it takes reality to completely break down. You're inside the black hole now, falling through a region of space where physics has become something between science and art. Above you, though above is becoming an increasingly meaningless concept. The entire external universe blazes in a ring of impossible brightness. Below, only darkness, growing deeper with each passing moment. But let's talk about that ring of light, because you're witnessing something that no conscious being has ever seen and lived to describe. The entire history of the universe, playing out in fast-forward, compressed into a single brilliant circle. The photon that ever fell into this black hole after you began your journey is now catching up. Light from distant galaxies that began its journey billions of years ago. Radio waves from the cosmic microwave background/long, the afterglow of the Big Bang itself, now blue shifted into visible light, then into X-rays, then into gamma rays so energetic they could sterilize planets. You're watching time itself compressed into light. The universe's past, present, and future, at least everything that falls into this black hole after your arrival, appears simultaneously in that blazing ring. It's like having front row seats to the cosmic movie theatre, where every film that was ever made is playing at the same time, at infinite speed, with the brightness turned up to 11. But here's what's really going to blow your mind. You're not just watching this light show, you're part of it. Remember, light that entered the black hole before you is still here, falling alongside you toward the singularity. If another traveler preceded you, maybe an astronaut from some distant civilization, or matter from a star that was consumed years ago, their light is creating ghostly afterimages throughout the space around you. Picture this. You might see the same person or object multiple times, each image representing a different moment in their fall. Recent images showing them just as they were when you arrived, older images showing them from earlier in their journey, all of these phantom figures falling through the darkness like a cosmic parade of the doomed. It's a museum of everything that ever fell into this black hole, preserved in light, all tumbling together toward the unknowable center. Every moment of the black hole's feeding history is here, frozen in the twisted geometry of space-time, visible only to fellow travelers on the same impossible journey. And if this black hole is rotating, which most are, the physics gets even more exotic. Rotating black holes create something called frame dragging, where space-time itself gets twisted like taffy. Imagine space as a thick liquid, and the black hole as a massive spinning object stirring that liquid into a whirlpool. Near the singularity, space itself is rotating so fast that it becomes impossible to remain stationary relative to the outside universe. In the ergosphere, that region outside the event horizon where space-time is dragged around, standing still becomes impossible. But inside the event horizon of a rotating black hole, the effects are even more extreme. Space itself is falling inward and spinning simultaneously, creating a cosmic tornado of geometry that defies every intuition about how reality should work. This rotation creates something that sounds like science fiction, but emerges directly from Einstein's equations, the ring singularity. Instead of matter being crushed to a point of infinite density, it might be compressed into an infinitely thin ring. And that ring? It might be a doorway. The mathematics of general relativity suggest that this ring could be an Einstein-Rosen bridge, a wormhole, connecting our region of space-time to somewhere else entirely. Maybe another part of our universe, maybe another universe altogether, maybe a region where time flows backward or the laws of physics work differently. Of course, whether anything could actually survive passage through such a gateway is an open question. The tidal forces near a ring singularity would still be extraordinary. But the mere possibility that black holes might be cosmic transit systems rather than cosmic garbage disposals is one of the most beautiful ideas in theoretical physics. But let's get back to your journey, because even in this impossible place, time keeps flowing and space keeps pulling you inward. As you fall deeper into the black hole, the visual effects become increasingly surreal. That ring of light from the external universe continues to brighten and blue shift. Light that started as gentle radio waves is now gamma radiation energetic enough to tear apart atomic nuclei. If your consciousness could somehow survive the experience, you'd be bathed in radiation carrying energies that dwarf anything found elsewhere in the universe. The irony is beautiful and terrible. Inside the darkest objects in the universe, you're experiencing the brightest light show that physics allows. The same gravitational field that makes escape impossible is creating visual phenomena that surpass anything else in nature. But beneath you, the darkness continues to grow. You're approaching the singularity, that mathematical point where all the mass that formed the black hole is theoretically compressed to infinite density, where the curvature of space-time becomes infinite, where our equations output infinity and essentially give up trying to describe reality. For decades, physicists have wrestled with what this means. Does matter really get compressed to a point with zero volume and infinite density? That seems unlikely. Infinities in physics usually indicate that we're missing something important, that our theories have reached their limits. Quantum mechanics suggests a different possibility. At the smallest scales, distances around the Planck length, which is about 10 to the minus 35 meters, space and time might not be smooth and continuous. Instead, they might be granular, made up of discrete units like the pixels on a computer screen. If that's true, then maybe the singularity isn't a point at all. Maybe it's a region where space and time become a foam of quantum possibilities, where the very concepts of location and moment lose their meaning. Maybe it's a place where matter doesn't get infinitely compressed, but instead transforms into something else, entirely, pure information, quantum probability, or forms of existence that don't have names in any human language. Some physicists have proposed even more exotic possibilities. Maybe singularities are cosmic recycling centers, where matter and energy get processed and eventually emerge as new universes through quantum tunneling. Maybe each black hole is actually a cosmic egg, gestating a new region of space-time with slightly different physical laws. If that's true, then your journey isn't ending at the singularity, it's beginning. You might be about to become part of the birth process for an entirely new cosmos, where the constants of physics, the properties of matter, and even the nature of time itself could be different from anything in our universe. But regardless of what the singularity actually is, your subjective experience of approaching it remains profoundly strange. Time, from your perspective, continues to flow normally. Your thoughts unfold at their usual pace. Your internal biological clock ticks along as if nothing unusual is happening. But the space around you is behaving in ways that would have seemed impossible just hours ago. Distances become meaningless near the singularity. The concept of how far breaks down when space-time itself is curved beyond recognition. You might feel like you're traveling a great distance, or you might feel like you're barely moving at all. Both sensations could be equally valid in the twisted geometry surrounding you. The tidal forces, depending on the black hole's mass and rotation, might be tearing you apart at the atomic level, or they might be surprisingly gentle, allowing you to maintain coherence almost until the very end. The mathematics depends on details we can barely comprehend, let alone observe. But here's something that might comfort you in these final moments. You're experiencing something that represents the absolute frontier of human knowledge. Every sensation, every visual effect, every twist of space-time you encounter is revealing secrets about the universe that no laboratory experiment could ever uncover. You're a cosmic explorer in the truest sense, venturing into a realm where space and time themselves are experimental subjects. The data from your journey, if it could somehow be transmitted to outside observers, would revolutionize our understanding of physics, consciousness, and the very nature of reality. In your final moments before reaching the singularity, you might experience something even more profound: the dissolution of the boundary between observer and observed, between yourself and the universe you're falling through. As the tidal forces stretch your consciousness across space-time, as the very atoms that once composed your thoughts get redistributed according to the iron laws of general relativity, you become part of the cosmic machinery itself. Your matter joins the singularity. Your energy contributes to the black hole's mass. Your information becomes entangled with the quantum state of one of the universe's most extreme objects. Some physicists argue that information cannot be destroyed, even at the singularity. If they're right, then everything that made you, every memory, every thought, every quantum state that contributed to your consciousness, becomes permanently encoded in the black hole structure. You don't disappear. You become part of something larger, more complex, and more fundamental than individual existence. Your information joins the vast library of everything that ever fell into this black hole, preserved in ways we don't yet understand, but can glimpse through the mathematics of quantum mechanics and general relativity. And if Hawking radiation is real, if black holes slowly evaporate by emitting particles over cosmic timescales, then you might not even stay trapped forever. Over googles of years, as the black hole slowly radiates away its mass, the information that was once you might be released back into the universe in subtle quantum correlations. You'd be scattered across space and time as gentle radiation, your essence distributed among photons and particles that carry forward the quantum signature of your existence. It's a kind of immortality that transcends anything religious or philosophical traditions have imagined, becoming literally one with the cosmos through the most extreme physics the universe allows. But that's a story for cosmic timescales that dwarf the entire current age of the universe. Right now, in these final moments, you're about to encounter the singularity itself, Eos, that point where our understanding of physics reaches its absolute limit. What happens next? We don't know. Maybe matter gets infinitely compressed. Maybe it tunnels through to another universe. Maybe it transforms into pure quantum information. Maybe the very question becomes meaningless in a region where space and time themselves break down. What we do know is this: you've taken the ultimate journey to the very edge of the knowable universe. You've experienced phenomena that stretch the boundaries of physics, consciousness, and existence itself. You've seen the universe's most extreme light show and participated in its most exotic dance of matter and energy. You've become part of the cosmic story in the most fundamental way possible, but our journey through the darkest mysteries of the universe isn't over yet. Because black holes don't just challenge our understanding of space and time, they create paradoxes that have kept the greatest minds in physics arguing for decades. Puzzles so deep and strange that they threaten to break our most fundamental theories about how reality works. Next time, we're going to explore the paradoxes that make Stephen Hawking argue with himself for 30 years. Contradictions so profound, they might force us to completely reimagine what we think we know about information, time, and the very nature of existence itself. Here's something that'll keep you awake at night. Black holes might be the universe's way of telling us that our most fundamental theories about reality are incomplete. And the proof? They create paradoxes so profound that Stephen Hawking spent 30 years arguing with himself about them. Let's start with the temperature paradox, because it's beautifully simple and completely mind-bending at the same time. When a massive star collapses to form a black hole, the process is violent beyond imagination. Matter gets compressed to incredible densities, space-time gets curved to extreme degrees, and temperatures during the collapse can reach hundreds of billions of degrees. In those final moments, the collapsing star is literally the hottest thing in the local universe. But then something strange happens. The event horizon forms, and suddenly, from the outside perspective, the black hole appears to have a temperature of absolute zero. Not cold, that's not a strong enough word. We're talking about a temperature so low it makes the cosmic microwave background seem like a raging furnace by comparison. For a black hole with the mass of our Sun, the Hawking temperature, the theoretical temperature associated with Hawking radiation, is about 6 billionths of a degree above absolute zero. That's colder than the space between galaxies, colder than anything that occurs naturally in the universe today. So how can the same object be simultaneously the hottest thing possible during its formation and the coldest thing possible after it's formed? It's like watching ice instantly transform into fire, except the ice and fire exist at the same time from different perspectives. But wait, it gets weirder. Stephen Hawking showed in 1974 that black holes aren't actually perfectly black. Quantum mechanics predicts that they should emit radiation, particles that slowly leak out from near the event horizon like steam escaping from a cosmic tea kettle. This Hawking radiation means that black holes are slowly evaporating, losing mass particle by particle over unimaginably long timescales. For a black hole with the mass of our Sun, complete evaporation would take about 10 to the 67 years. That's a number so large it makes the current age of the universe, a mere 14 billion years, look like a brief hiccup. We're talking about timescales where the word forever starts to feel inadequate. But here's where the temperature paradox gets really twisted. As a black hole evaporates, it gets hotter. Smaller black holes have higher Hawking temperatures. A black hole with the mass of Mount Everest would have a temperature of about 1 billion degrees and would evaporate in less than a second in a burst of energy that would make nuclear weapons look like firecrackers. So, black holes are simultaneously the coldest and potentially the hottest objects in the universe, depending on their mass and how long you're willing to wait. It's like the universe can't make up its mind about what temperature means near a black hole, but that's just the appetizer. The main course is the information paradox, and it's a dish that's been giving physicists indigestion for decades. Here's the setup. Imagine you have a book. Let's say it's a complete encyclopedia containing all human knowledge. You throw it into a black hole. What happens to the information in that book? Classical general relativity says the information falls past the event horizon and eventually reaches the singularity, where it's presumably destroyed along with everything else. The information is gone forever, erased from the universe. But quantum mechanics has something to say about this, and it's not happy. One of the fundamental principles of quantum mechanics is that information cannot be destroyed. It can be scrambled, encoded, transformed beyond recognition, but never truly eliminated. The total amount of information in the universe must remain constant. So we have a problem. General relativity says the information is destroyed. Quantum mechanics says it can't be. Both theories have been tested extensively and work beautifully in their respective domains. But black holes force them into direct conflict. Hawking originally sided with general relativity. He argued that black holes really do destroy information, and quantum mechanics would just have to deal with it. This was a radical position, essentially saying that one of the most fundamental principles of quantum theory was wrong. But in 2004, Hawking changed his mind. He conceded a famous bet with physicist John Preskill, admitting that black holes probably don't destroy information after all. But this created an even bigger puzzle. If information isn't destroyed, where does it go? How does it escape from inside a black hole? Hawking's proposed solution involved something called supertranslations, quantum mechanical processes so subtle and complex that most physicists admit they don't fully understand them. The idea is that information might be encoded in the correlations between Hawking radiation particles in ways so sophisticated that it would take quantum computers the size of planets to decode the original information. Imagine trying to reconstruct the complete text of that encyclopedia by analyzing the subtle statistical patterns in what appears to be random static. The information is there, but retrieving it would require computational power that dwarfs anything we can currently imagine. But even this solution creates new paradoxes. If information does somehow escape through Hawking radiation, it creates what's called the firewall paradox. Here's the problem. For information to escape, the particles near the event horizon would need to be quantum mechanically entangled with particles that escaped earlier. But this entanglement would require enormous amounts of energy, enough to create a firewall of high-energy particles right at the event horizon. If firewalls exist, then falling into a black hole wouldn't be the gentle experience we described for supermassive black holes. Instead, you'd be incinerated the instant you crossed the event horizon, burned to death by a wall of ultra-energetic particles created by quantum entanglement. This contradicts Einstein's principle of equivalence, which says that falling freely in a gravitational field should feel the same as floating in empty space. No sudden walls of fire, no dramatic boundaries, just smooth space-time curvature. So we're stuck with an impossible choice. Either information is destroyed, violating quantum mechanics, or firewalls exist, violating general relativity, or some completely new physics is required to resolve the paradox. And it gets worse. Recent observations have found black holes that theoretically shouldn't exist. Intermediate mass black holes weighing thousands of solar masses, filling the gap between stellar mass and supermassive black holes. The problem is, we don't have good theories for how such objects could form. Stellar mass black holes come from massive star collapse. Oh, we understand that process. Supermassive black holes probably grew from smaller, seed black holes in the early universe. We have plausible models for that too. But intermediate mass black holes? They're orphans in our theoretical family tree, existing without a clear explanation for their birth. Then there are primordial black holes, objects that might have formed in the first fraction of a second after the Big Bang, before the first stars ever existed. These could range in mass from microscopic to thousands of solar masses, and if they exist, they could solve several cosmic mysteries. Primordial black holes could be the dark matter that makes up 85% of the universe's mass. They could explain why supermassive black holes existed so early in cosmic history. They could even be wandering through our solar system right now, invisible and undetected. But here's the thing that really messes with your head. We might be living inside a black hole right now. I know. That sounds crazy, but some cosmologists have seriously proposed that our entire observable universe could be the interior of a supermassive black hole. The Big Bang might not have been the beginning of everything, but rather the moment we crossed an event horizon into a larger cosmic structure. Think about it. From inside a black hole, you can't see the external universe. You can't escape back to where you came from. Space itself expands as you fall toward the singularity. Sound familiar? These are also properties of our expanding universe. The math actually works. A universe inside a black hole would expand at exactly the rate we observe, would have the critical density we measure, and would evolve in ways consistent with cosmic microwave background observations. It's a disturbing possibility that can't be easily dismissed. And then there's the music. Black holes sing. The supermassive black hole at the center of the Perseus galaxy cluster produces actual sound waves, acoustic vibrations traveling through the hot gas surrounding it. The frequency? B-flat, 57 octaves below middle C. This cosmic bass note has been playing for over 2 billion years, making it not only the deepest sound in the universe but also the longest-running musical performance in cosmic history. The black hole is literally conducting a symphony of gas and plasma on scales that span hundreds of thousands of light years. But why does it sing? The sound waves are created by jets of material shooting out from near the event horizon at 99% the speed of light. These jets punch cavities in the surrounding gas, and the cavities oscillate like organ pipes, creating pressure waves that travel through the cosmic medium. It's beautiful and strange. Objects that represent the ultimate silence, regions where even light cannot escape, are also cosmic musicians, playing notes so deep that human ears could never detect them. All of these paradoxes and discoveries point to an uncomfortable truth. Black holes are revealing that our understanding of physics is incomplete. They're showing us places where our best theories break down, where the universe behaves in ways that challenge our most fundamental assumptions about how reality works. Maybe information really is destroyed, and we need new quantum mechanics. Maybe space-time really does have firewalls, and we need new general relativity. Maybe we need entirely new physics that unifies quantum mechanics and gravity in ways we haven't imagined yet. Or maybe black holes are trying to tell us something even more profound, that the universe is stranger, more complex, and more wonderful than any theory we've developed so far. But here's the twist that's going to completely change how you think about these cosmic monsters. Everything we've discovered about black holes, all the paradoxes, all the extreme physics, all the reality-bending behavior, has led to the most surprising revelation of all. Black holes aren't destroyers, they're creators. They're not cosmic vacuum cleaners sucking up matter and energy. They're cosmic gardeners, cultivating the conditions that made your existence possible. Next time, we're going to explore the most mind-blowing discovery about black holes. They didn't just happen to exist in our universe. They helped build it. Every atom in your body, every star in the sky, every galaxy in the cosmos exists because black holes shaped the cosmic environment in ways that made complexity, chemistry, and life itself possible. Get ready to discover why the monsters we feared might actually be the mothers of all existence. Here's the twist that's going to completely flip everything you thought you knew about black holes. They're not cosmic destroyers, they're cosmic architects. Every atom in your body, every star you've ever seen, every galaxy scattered across the cosmic web exists because black holes helped build the universe into a place where complexity and life could emerge. I know it sounds impossible. We've spent this entire journey talking about objects that warp space-time, devour light, and create paradoxes that break physics. How could these cosmic monsters be responsible for your existence? Well, buckle up, because the universe is about to reveal its most beautiful secret. Let's start with a number that'll blow your mind. 4 million. That's roughly how many times more massive the black hole at the center of our galaxy is compared to our Sun. Sagittarius A star, sitting about 26,000 light-years away, weighs as much as 4 million suns compressed into a region smaller than Mercury's orbit. Now, here's the crazy part. The mass of that central black hole is directly related to the mass of our galaxy's central bulge of stars. It's not a coincidence. There's a fundamental relationship between the two that holds across the entire observable universe. Every large galaxy has a supermassive black hole at its center, and in every case, the black hole's mass is about 0.1% of the central stellar bulge's mass. Always. It's like the universe has a cosmic building code that requires specific ratios between black holes and their host galaxies. This suggests something profound. Black holes and galaxies didn't just happen to end up together. They grew up together, each one influencing the other's development over billions of years. The black hole helped shape the galaxy, and the galaxy helped feed the black hole. But how? Picture the early universe, just a few 100 million years after the Big Bang. It's a very different place from today, too smaller, denser, filled with pristine hydrogen and helium gas that's never been processed by stellar nuclear fusion. There are no heavy elements yet, no carbon or oxygen or iron, just the simplest atoms floating in the cosmic dark. In this ancient cosmos, the first massive stars are forming and dying in spectacular supernovae. Some of these stellar explosions leave behind black holes the first black holes in the universe's history. And these primordial black holes become cosmic seeds around which everything else can grow. Here's where the physics gets beautiful. Black holes don't just consume matter randomly. When gas falls toward a black hole, it doesn't just quietly disappear down the cosmic drain. Instead, it forms an accretion disk, a swirling maelstrom of superheated material that becomes one of the most energetic objects in the universe. As matter spirals inward, friction heats it to millions of degrees. The material doesn't just glow, it screams across the electromagnetic spectrum, producing radio waves, X-rays, and gamma rays. But here's the really important part. Not all of that material actually falls into the black hole. About 10% of the infalling matter gets launched back into space in the form of relativistic jets, streams of particles moving at 99% the speed of light, shooting thousands of light years away from the black hole in opposite directions. These jets are cosmic gardening tools. When a jet slams into the surrounding gas at nearly light speed, it creates shock waves that compress the gas into denser regions. These compressed regions become the seeds for new star formation. The jet also carries magnetic fields that help organize the gas into the large-scale structures we see today. Essentially, black holes are cosmic sculptors, using jets of high-energy particles to carve gas into galaxy-shaped workshops where stars can form efficiently. But there's more. Those jets also carry heavy elements: iron, carbon, oxygen, iron, silicon, forged in the nuclear furnaces of massive stars before they collapse to form the black hole. When the jets deposit this material throughout space, they're seeding the cosmos with the building blocks of planets and life. The iron in your blood was created in the core of a massive star. The calcium in your bones was forged in stellar nuclear fusion. The oxygen you're breathing right now was produced when ancient stars fused helium nuclei together. But all of these elements only became available for planet formation because black hole jets distributed them across vast regions of space. Without black holes acting as cosmic recycling centers, heavy elements would remain locked up in stellar cores. The universe would be filled with only hydrogen and helium, no rocky planets, no complex chemistry, no life as we know it. But black holes do something even more fundamental. They help determine where and when stars can form in the first place. In the early universe, gas was distributed relatively smoothly throughout space. For stars to form, that gas needs to clump together under its own gravity. But here's the problem. If gas clumps too quickly, it heats up, and the thermal pressure prevents further collapse. If it doesn't clump fast enough, the expansion of the universe pulls it apart before stars can form. Black holes provide the gravitational anchors that allow gas to clump together at just the right rate. Their immense gravity creates deep gravitational wells that can collect and hold gas even as the universe expands around them. They're like cosmic cities, dense population centers that attract matter from across vast regions of space. The supermassive black hole at the center of our galaxy has been performing this cosmic urban planning for over 10 billion years. It helped determine where in the Milky Way stars could form efficiently, which regions would become stellar nurseries, and which areas would remain relatively empty. Our Sun formed in one of these star-forming regions about 4.5 billion years ago, in a neighborhood of the galaxy whose properties were ultimately determined by the gravitational influence of Sagittarius A star, the stable, roughly circular orbit that keeps our solar system in the galactic habitable zone. That's possible because of the organized structure that supermassive black holes help create. Even more amazing, the timing of star formation in our galaxy was influenced by black hole activity. Periods when the central black hole was actively feeding correspond to bursts of star formation throughout the galactic disk. Quiet periods when the black hole was dormant correspond to lulls in stellar birth rates. It's like the black hole at the center of our galaxy has been conducting a cosmic symphony of star formation for billions of years, determining not just where stars form, but when they form. And here's something that'll really blow your mind. Black holes might be the only objects in the universe capable of outliving everything else. Through Hawking radiation, black holes slowly evaporate over cosmic timescales. But these timescales are so vast, they make the current age of the universe seem like a brief moment. A black hole with the mass of our Sun would take about 10 to the 67th years to evaporate completely. To put that in perspective, by the time stellar mass black holes finish evaporating, the universe will be so old that all the stars will have burned out, all the protons will have decayed, and even atomic nuclei will have fallen apart. Black holes will be the last remaining objects in a cold, empty cosmos. In the final phase of cosmic evolution, when the universe is a trillion times older than it is today, the only remaining sources of energy will be the gentle glow of Hawking radiation from evaporating black holes. They'll be the universe's final campfires, providing the last bit of warmth in an otherwise frozen cosmos. But even this ending might not be an ending. Some physicists propose that black holes are cosmic eggs, that each singularity might birth a new universe through quantum tunneling effects. If this is true, then when our universe's black holes finally evaporate, they might leave behind baby universes, each with slightly different physical constants and laws of nature. Our universe might exist because a black hole in some previous cosmic generation created the perfect conditions for atoms, stars, planets, and life to emerge. The monsters we feared might be the mothers of all existence, midwiving new realities into being through processes so exotic we can barely comprehend them. And if that's true, then the universe isn't just stranger than we imagine. It's a cosmic family tree, where black holes serve as both the graveyards of old realities and the nurseries of new ones. Think about the profound beauty of this story. The same objects that represent the most extreme physics in our universe, regions where space and time break down, where causality gets twisted, where our understanding of reality reaches its limits, are also the cosmic gardeners that made our existence possible. The black hole at the center of our galaxy helped organize the gas that became our solar system. The jets from ancient black holes distributed the heavy elements that became the planets, the oceans, and eventually us. The gravitational influence of supermassive black holes helped create the stable, long-lived cosmic environments where billions of years of evolution could unfold. We exist in the Goldilocks zone not just of our solar system, but of our galaxy, a region where star formation, heavy element abundance, and gravitational stability are all just right for the emergence of complexity and life. And all of these conditions trace back, directly or indirectly, to the influence of black holes. It's a story of cosmic symbiosis that spans 14 billion years. Black holes shaped the universe. The universe fed the black holes. Together, they created the cosmic conditions where matter could organize itself into molecules, cells, organisms, and eventually, conscious beings capable of wondering about their own existence. You are literally made of star stuff that was organized by black holes. Every breath you take contains oxygen forged in stellar cores and distributed by black hole jets. Every thought you think is enabled by carbon atoms that traveled through the cosmos for billions of years, guided by the gravitational influence of these cosmic architects. The universe's most fearsome objects turn out to be its most nurturing parents. The cosmic monsters that warp space-time and swallow light are also the cosmic gardeners that cultivated the conditions for minds capable of understanding their own cosmic heritage. From John Mitchell's dark stars to Event Horizon Telescope images, from Schwarzschild's impossible mathematics to Hawking's quantum revelations, we've discovered that the universe is far stranger and more wonderful than our ancestors could have imagined. And at the heart of this cosmic story are black holes, not as endings, but as beginnings. They're the universe's way of creating complexity from chaos, structure from randomness, and ultimately, consciousness from matter. In the deepest sense, black holes didn't just help build your atoms, they helped build the cosmic stage on which the drama of existence could unfold. And that might be the most beautiful secret the universe has ever revealed. The objects we thought represented the ultimate darkness are actually the hidden architects of all the light we've ever known.